I actually changed the title a little bit. It says, was the Big Bang a fizzle? In reality, I don't think the Big Bang ever happened. So the real question is the Big Bang theory a fizzle? Modern cosmologists would have us believe that 13.75 billion years ago, a spot of infinite density and infinite temperature and infinitely small, for some inexplicable reason, exploded in an event now known as the Big Bang. One way to put it is that in the beginning, there was nothing, and then nothing exploded. Now, scientists have spent a lot of time working on this Big Bang theory, and they've taken it down to an incredible amount of detail. And here's a short extract. I'll just read this from Wikipedia. I hope you don't fall asleep on me. Approximately 1 trillionth of a trillionth of a trillionth of a second after the Big Bang happened, and we got into the expansion phase of the Big Bang, a phase transition caused a cosmic inflation during which the universe grew exponentially. After this inflation stopped, the universe consisted of quark-gluon plasma as well as all the other elementary particles. Now, I don't know about you. When I first was introduced to this theory, I was flabbergasted. Who in the world has the hubris to think that they can ascertain what happened in the first trillionth of a trillionth of a trillionth of a second of an event that occurred 13.75 billion years ago? Now, there are cosmologists that have spent their entire career lecturing on this subject, writing books about the subject, teaching their students, grading their grades, deciding whether or not they're going to advance in their careers based on whether or not they support this subject. And billions have been spent on machines to try to figure out whether the theory is correct. We built the Large Hadron Collider. We have incredible telescopes that have been put up. And we have space probes. And they're just trying to iron out the last few minor little details about this theory. Here's a graph. Here's a graph showing part of the progression. And it's kind of hard to read. But up here we start at 10 to the minus 43 seconds. On up to the 10 to the minus 10th seconds. Finally, at about 300,000 years, we actually start creating atoms, complete atoms. And then we get into about 1,000 million years after this occurred, we start getting into galaxies. There's a lot of different charts and things you can find on this theory, and there's a wide variety of theories actually out there. But I got to say that as a person who was very interested in science and wanted to study science as a child, I was a little bit jaded by the whole thing, and I started thinking that maybe there's a better career. So I'm much different than a lot of the presenters here. I don't have a degree in physics. I haven't written any books. And after trying school 3 different times, I never really made it through. But I've read hundreds of books. I have enough credit hours to get several degrees. But what happened was, when I was a kid, and this is my story, is I found out about Immanuel Velikovsky, and I know a lot of people here kind of got their start into this direction with Immanuel Velikovsky. And he taught me several things. One thing is that the scientists that are out there that are publishing all these documents really may not know everything. I also learned that in order to derive a complete theory about everything, you have to include everything. So you can't ignore what the religions and the myths and the geologists and the archaeologists are saying if you're going to create a theory describing the creation of the universe. So a full understanding requires that we take into account everything that we've learned. I also learned from Velikovsky that if you're going to come out with a new theory or something that opposes the mainstream thought, it's not going to be accepted easily. And in fact, Velikovsky was vilified for what he wrote. People refused to read his work or even consider it. And the Velikovsky affair, where they talk about science not being able to accept his theory, is actually a bigger story than what Velikovsky himself wrote. In high school, I was asked to do a report on a fiction book, and I told my teacher I thought that was a waste of time. And I asked her if I could do an autobiography on Einstein instead. And she went ahead and let me do it. And there was a quote in there, and it said that when Arthur Stanley Eddington was asked how it feels to be one of the only 3 people who understand relativity, he answered, who's the third? Now, I'm a farm boy from Colorado, and I read this and I thought, how in the world will I ever be able to contribute to that line of thought? So instead, I figured that maybe I should get into something a little more real, and I thought maybe designing toasters would be a lot more rewarding than studying quantum mechanics or black holes. So I got a job in the semiconductor industry as an electrical engineer, and I ended up working a lot with statistical analysis of data, trying to find patterns automatically. In semiconductors, there's a massive amount of data, and a lot of it never gets looked at, so I created programs that would try to find, and here you see in the middle, a pattern that shows up. I also got a chance to look into plasma etch equipment, and plasma is used extensively in semiconductor manufacturing to create the integrated circuits that are in our phones and our TVs and everything else. And here's an example of a plasma etch equipment. It was kind of fun. I got to change gas compositions, temperatures, RF power, and just play around with it. I spent hundreds of hours looking into these. And when I looked up and saw the Twin Jet Nebula, it became apparent to me that this is not an exploding supernova. This is a plasma formation. I now do contract work working with highly sophisticated websites that are data and media intensive, so if anyone needs something like that, just give me a call. But I very clearly remember, though, about 5 years ago when I was reading on the internet and discovered the electric universe theory. And this brought it all back to me. This brought back the joy of science and exploration. It was no longer the science of the advanced mathematics that no one else can understand. Instead, it brought it back to the science that creates this modern world. It's the electromagnetism that we know about in our motors and generators and oscillators, transmitters, receivers. All the things that have created our modern world are incorporated into the electric universe theory. It's no longer something that is only the gods of the mathematics or the high-end mathematic people that can understand. Even a mere mortal like myself could understand this. And I like to talk. I like a microphone. It's fun to get up in front of a group. So I started talking about the electric universe. And as a member of Toastmasters, I had to give weekly presentations. And I started kind of branching out and doing service groups like the Rotary Group and Lions Group, and I belong to a couple spiritual groups, and they're all excited about this. And so I started giving presentations, and I kind of boiled this down. Now this will be an oversimplification, but I boiled down the two major ideas I see that are wrong with cosmology today into two concepts. And one of them is that gravity is the primary force that shapes the universe, and electricity plays no role. Now, there's a bunch of presentations on this. You're going to hear about them from other people. These are kind of some of the ideas that have fallen out of that, and I'm really not going to cover this any farther. But there's another idea which I felt never really was covered adequately in these conferences, and that's the idea that redshift can be used to measure velocity and therefore can be used to measure distance. So when you hear that a galaxy or a quasar or some object has been found that's 100 million light years away, this is the method they're using to measure that. And so some of the ideas that fall out of that is that the universe started with the Big Bang, and that's because we believe that the universe is expanding, and if it's expanding, then at some point it must have all been back together at one point. So there was a start to the universe. And it's been expanding ever since, after the Big Bang. And then they discovered that the rate of expansion appears to be increasing. And if the rate of expansion is increasing, an anti-gravity-like force is pushing the universe apart. And they called this dark energy. And then another conjecture that kind of is predicated all of this is that matter is the same across the universe. And this means that a proton weighs the same here in our galaxy as it does in another galaxy as it does anywhere else. Now, I don't know anyone that's ever sampled another galaxy and actually measured a proton in one of these other galaxies, but this is a very strong underpinning to this whole story of redshift. So you might ask, what is redshift? Well, back in 1842, a gentleman named Christian Doppler took a train, a flatbed, and put a band on it and ran it by some observers, and they would listen to it, and they all had perfect pitch, I guess, and they would listen to the change in pitch. And the idea is with sound is that when a train goes by, you hear a train go, you don't actually need the band, you can forget the band, but when a train goes by, you hear it and it goes, na 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 na, and it drops in pitch. Or another idea is a car. When you hear a car go by, it goes, phew, phew. Whereas you never hear a car go, phew. So there's a drop in pitch, and the same thing happens with light. Light is just another example of something vibrating. And up here in this first picture, if you imagine that this galaxy here is stationary, and we are on the Earth looking at it, and we see an absorption line. So there's a dark spot that shows up in the spectrum, and in this case, we'll just put it in the middle, because that's a good way to do this example. In this case, we have a galaxy that's moving away from us, and that effectively lengthens out this wave a little bit, and that causes the light to shift a little to the red, or a little bit slower frequency light. Likewise, if you have an object moving towards us, then it's going to shift a little bit to the blue. Now, as it turns out, almost every object we see outside of our galaxy is shifted red. There are very, very few objects that are blue shifted or moving towards us. And that's why we believe in the expanding universe. This came about with Milton Humason back in 1927, discovered that these remote galaxies were redshifted. And then Georges Lemaitre, and I probably just clobbered that, was a Belgian priest, and he actually proposed this Big Bang theory. And then finally, in 1929, Edwin Hubble, who the Hubble telescope's named after, proposed Hubble's law. And there's really two parts to the law, and that's all objects in deep space are redshifted. And that's not quite, there are a couple that are blue shifted. But then also from that, he determined that this redshift is proportional to their distance to Earth. So once again, when you hear about objects that are 100 million light years away, that is coming from this idea of redshift. Carl Sagan actually in Cosmos in chapter 10 quoted, and I had to cut out a bunch of what he wrote because Carl Sagan can really talk a lot. And I'm not sure he says a lot sometimes. But the main point is that Halton Arp has found enigmatic and disturbing cases where a galaxy and a quasar that are in apparent physical association have very different redshifts. And if this is the case, if a object is, the quasars are supposed to be at the very edge of the galaxy or the universe. They're so far away, they're 12 billion light years away according to conventional cosmology. And if for some reason you can see a relationship with an alleged nearby object, then something's wrong with the whole idea of redshift. And this is actually, I should clarify, is recessional redshift, or a redshift of an object moving away or away from us or towards us. There are other types of redshift. There's gravitational redshift. There's thought to be, we'll get into a third one here in a second with ARP. But at the end it says ARP, if ARP is right, the exotic mechanisms proposed to explain the energy of these distant quasars would prove unnecessary. Now, these quasars are allegedly at the edge of the universe, and yet we can still see them. And if we can see them, they must be incredibly powerful. And it was brought up last night about a quasar that was thought to be 12 billion light years from us. And the web says that it's 20 billion times the size of our sun, has a mass of 20 billion times that of our sun. And there thought to be this water cloud around it of 140 trillion times that of the Earth's oceans. And it emanates the energy, I thought this was incredible, emanates the energy equivalent of 100 trillion of our suns. Now this all comes from the idea that it's 12 billion light years away. If it happens to be much, much, much closer, then suddenly this could be just a normal object. It doesn't have to be anything this incredible. Because quasars are thought to be the most luminous, most powerful and energetic objects known in the universe. And then this brings us to the whole point of this presentation is Halton Arp. Halton Arp went to school in Harvard and then got his PhD at Caltech. And he actually did some work for Hubble in his early career looking for novas. He worked at Mount Wilson and Mount Palomar as a staff astronomer. So he wasn't a cosmologist sitting at his supercomputer doing simulations. He actually looked through telescopes. And he created the ARP, Atlas of Peculiar Galaxies, showing 333 galaxies that he thought didn't fit the model that most people believed in. He wrote several other books about redshift, and a lot of this presentation is taken from this book here, Seeing Red. So what's his evidence? And there's a lot of different evidence. I just have a couple of them up here, the main ones here. But one of the main pieces of evidence is that he has found pairs of quasars on opposite sides of nearby galaxies. And once again, the quasars are far away. The galaxies are very close. How is it that these quasars could be related to this close-by galaxy? Here's an example. This is IC 1767. It's called a Seyfert galaxy. A Seyfert galaxy is known to emit lots of X-rays and radio waves. And they found these two quasars right next to it. Now, what's odd about this is that these numbers here, this 0.616 and 0.669, are indicators of the redshift. And if it's a positive number, that means that it's redshifted, is moving away from us. If it's a negative number, it's blue shifted and moving towards us. And these two redshifts are extremely close. And the probability of finding two quasars opposite a central galaxy with an extremely close redshift is very, very low. And I don't remember the exact numbers on this, but I know he quotes numbers 1 in 10,000, 1 in 100,000 for some of these different examples I'll show you. So the conventional astronomy said, well, yeah, but you know, it's almost impossible to win the lottery too, but people win the lottery, and they're right. So maybe there's other proof. Now, I actually thought this was about quasars. As it turns out, these are clusters of galaxies showing the same type of effect. If you look, this is the redshift of this item is 0.55, and the redshift of this item is 0.59, and the redshift of the central item is 0.014. So once again, we have two objects on opposite sides of a central, in this case, a pair of galaxies. But it shows another example where there's a galaxy in the middle of two other objects, in this case, other clusters of stars. Here's a third example. We have these two central galaxies here in the middle, N474 and N470. And opposite it, we have two quasars. We have one with a redshift of 0.672 and a fairly close redshift of 0.675. Now, it's starting to get a little odd that we keep seeing this exact relationship. So if you would imagine that the central galaxy here now is a blue house. We'll go back to the lottery analogy. We have a blue house in the middle, and we have twin daughters living on each side of the house. Now, how often are you going to find that the lottery winner always lives in a blue house and has twin daughters living on each side? Here we have another example of NGC 2639. The two quasars have redshifts of 0.307 and 0.325, so we have yet another family that's lucky here. Here we have another example with M95 in the middle. It has two quasars on each side of 0.033 and 0.036. Now, one thing I haven't brought up is that not only are these galaxies, or these quasars, found as pairs on opposite sides of a central galaxy, but they are found on the minor axis of that central galaxy. And this is usually plotted as Halton Arp, when you read his information, was surprised when he would be hoping, of course, that he'd find that, but it happens again and again and again. Here's a little bit different picture. We have a lot of items, by the way, in space are named after Halton Arp. He was a very famous astronomer. At one point, he was rated as being one of the top 20 astronomers in the world, and then he started saying that the theory of redshift was incorrect, and he was dropped off the chart. But here we see two items again with a redshift of 1.25 and 1.26, very, very close redshifts, found opposite this central galaxy, ARP 220. So, you know, the individual charts are, to me, convincing enough, but since I did a lot of work in semiconductors looking at statistics, this chart, I don't see how anyone can refuse this chart. And it shows the relationship of the brightness of different quasars and the brightness of a Seyfert galaxy. And the correlation is astounding. This is a 1 in 10 million chance according to Halton Arp, that this is accidental. And to me, he has some other charts showing the same type of information. And of course, the way the conventional scientists answered this was by not looking at it. So then he started realizing, well, maybe there's a little more going on here than just quasars. And he started looking around, and he found many, many examples where we have a central galaxy. The central galaxy's minor axis is plotted here. And we see all these quasars, or some of them aren't quasars, but I think in this case they are. And you find out that they're fairly well aligned along this central axis. Not only that, but the closest object, this one has a redshift of 2.1, 1.4, 0.83, 0.69. I should have brought my glasses. 0.33. So as you go farther and farther away from the central galaxy, it turns out the redshifts go off and drop off and become less and less. And his conclusion from this is that we have a central galaxy here in the middle, and these central galaxies are actually ejecting these quasars, generally in pairs, not all the time, but for the most part in pairs. And so the quasar starts out with a very high redshift when it's immediate at the point of ejection, and as it proceeds outwards, the redshift drops off lower and lower and lower. It reaches a point where the gravity of the central galaxy begins to pull it back, and it starts to come back into the central galaxy, and at that point it has a redshift very close to that of the central galaxy. He believes that at this point of ejection, when the quasars are ejected, they actually have no mass. So this gets back to the assumption we had earlier, where protons throughout the universe weigh the same regardless of where they are. In his theory, they are very different. They actually start out with a mass of 0, which makes it very easy for them to eject. And due to the fact they have a mass of 0, that's what is causing the redshift. And his term for this was intrinsic redshift, instead of the recessional redshift that Edwin Hubble talked about. Well, this extended even further. It kind of got to the point, a lot of people say that Halton Arp cherry-picked his evidence, and that he was looking for these specific examples where there were blue houses with twins living on each side, and they won the lottery. But it really got to a point where people would say, well, I found a pair of X-ray sources, or I found a pair of quasars, or I found a pair of, in this case, galaxy clusters. And Halton Arp would go, oh, well, then let's look in between them and find the Seifert galaxy in the middle. So I think that instead of him cherry-picking the data, it's almost like the data picked him. So this is one type of evidence. And there's a lot of examples. If you read through his book, Intrinsic Redshift, you'll find dozens and dozens more. And I'm sure that he actually found many, many more examples than that. But what's another type of evidence is that he actually found visible connections between alleged nearby galaxies and faraway quasars. And an example of this is Markarian 205, you see at the bottom. Now and it's associated with this galaxy NGC 4319, and the N4319 has a redshift of 0.006, which means it's not hardly redshifted at all, whereas Markarian has one of 0.07. This is a significant difference. They should be very, very far apart in distance from us. But there's this luminous bridge that apparently connects them. He's found these luminous bridges visible. He's also found them in X-ray, and they are now finding these luminous bridges in gamma rays. But the idea is that, well, this is just a coincidence. We're not really seeing what we think we see. And what does it all mean? One, redshift is not, the recessional redshift is not an indicator of velocity, but it's really an indicator of age. Second of all, quasars are not super bright, incredibly energetic objects. They're very close. The third one is really don't know the age of the universe. We don't know if it started, we don't know if it ended, and we will probably never know. We don't know the distance to many extra galactic objects, and we really can't see as far as we think. We think we're seeing 12 billion light years out. We may only be seeing into our local neighborhood. The Big Bang didn't happen. Quasars are actually young galaxies, and they're being expelled. And it's also, if you look at some of his equations, he would say that general relativity is no longer needed to explain the galaxy. Now, he really doesn't talk about the electric universe a lot in his writings, but I know that at the end he pretty much embraced that this probably explains a lot of his ideas. And He's often being called the modern Galileo because Galileo looked through a telescope and kind of got in trouble with the orthodoxy of the church. Halton Arp looked through a telescope and got in trouble with the orthodoxy of modern cosmology. Both of them said we aren't the center of the universe and we're not the focal point, which I really didn't get into that proof. But in the end, though, Galileo won out. And I would say that in the end, Halton Arp will also win out, and he will get the last laugh. Thank you. I actually changed the title a little bit. It says, was the Big Bang a fizzle? In reality, I don't think the Big Bang ever happened. So the real question is the Big Bang theory a fizzle? Modern cosmologists would have us believe that 13.75 billion years ago, a spot of infinite density and infinite temperature and infinitely small, for some inexplicable reason, exploded in an event now known as the Big Bang. One way to put it is that in the beginning, there was nothing, and then nothing exploded. Now, scientists have spent a lot of time working on this Big Bang theory, and they've taken it down to an incredible amount of detail. And here's a short extract. I'll just read this from Wikipedia. I hope you don't fall asleep on me. Approximately 1 trillionth of a trillionth of a trillionth of a second after the Big Bang happened, and we got into the expansion phase of the Big Bang, a phase transition caused a cosmic inflation during which the universe grew exponentially. After this inflation stopped, the universe consisted of quark-gluon plasma as well as all the other elementary particles. Now, I don't know about you. When I first was introduced to this theory, I was flabbergasted. Who in the world has the hubris to think that they can ascertain what happened in the first trillionth of a trillionth of a trillionth of a second of an event that occurred 13.75 billion years ago? Now, there are cosmologists that have spent their entire career lecturing on this subject, writing books about the subject, teaching their students, grading their grades, deciding whether or not they're going to advance in their careers based on whether or not they support this subject. And billions have been spent on machines to try to figure out whether the theory is correct. We built the Large Hadron Collider. We have incredible telescopes that have been put up. And we have space probes. And they're just trying to iron out the last few minor little details about this theory. Here's a graph. Here's a graph showing part of the progression. And it's kind of hard to read. But up here we start at 10 to the minus 43 seconds. On up to the 10 to the minus 10th seconds. Finally, at about 300,000 years, we actually start creating atoms, complete atoms. And then we get into about 1,000 million years after this occurred, we start getting into galaxies. There's a lot of different charts and things you can find on this theory, and there's a wide variety of theories actually out there. But I got to say that as a person who was very interested in science and wanted to study science as a child, I was a little bit jaded by the whole thing, and I started thinking that maybe there's